think about a question. You have your airplane, and each time you fly, if you have an emergency and when you want to do an emergency landing, you're going to look at this diagram, which airport is the nearest airport, or which spot is the nearest spot. Or you are in the campus, you have an emergency, look for an emergency call, you don't have a cell phone, and what you're going to do, you're going to look at the nearest location, have the phone, and then if those are all the phone, and then those sites, if anybody here is the closest to here, any here is closest to here, or say emergency center. If you have an emergency, you want to send it to the emergency center, in which region you'll go to which center. That's how, you see, if you look at these 2 points, this is the bisection line. Can you see it? You know, this distance is equal. You know, the distance to this is perpendicular to this line, equal distance. Can you see that? No? If you connect the A and the B, you get a vertical line to this border. Can you see it?
Are you saying that all those lines are just the network?
Yeah, it's a network.
Drop down between the points?
Yeah.
As the nearest?
Yeah.
These are your spaces between your points.
Think about another way. If you get the first file, you have one file sent from here, start here, one first file start from here. This file spread in the same speed. They're going to burn and spread the territory, and then the 2 files will meet here in this line. Did you see that? And the crystal grow in the same way with this kind of diagram. They're going to grow in the same speed and then meet the boundary, and that's how they looks like those shapes. And usually this diagram is on average is 5 to 6 edges. And then another dual concept is called the dynamic triangulation. And our surface rendering in geometry, we use the dynamic triangulation. The dual are just the size of this. If you do the perpendicular line, you got all the triangles, see? It's called the dynamic triangle. It's very useful. How useful? You go all the way from the A to Z, geology or agriculture, whatever, because it's the distance, neighborhood, similarity. You count. You know that has amazing many applications and reinvented from all different terminology actually. You know? So that's the concept we're using. Sometimes it's not in the mainstream calculus, but very useful. That's what we usually do in the undergraduate research. You have not learned it, but it's very useful. In here, look at that case. How do you get K? Of course, it's important, but nobody tells you unless you find it. Now, intuitively, you're going to see when you visualize it, that case is not a good option, right? Too big. You might think that this is the good choice. Even include one of those is fine. But the expand this are too big, right? So when you visualize, you probably think that this case should be 7 or 5, either way. So use the graphic feature to draw it. And this is also, I tell you, if it's too big, the board is very hard to control. You can expand a little bit bigger, then you will change class again, right? That's not a good choice. A good choice should be here. But it depends. You don't just look at that case. Maybe somewhere else you need a little bigger, right? You need to look at the total. The choice of the distance, actually, before you choose the distance, only any data mine. The first choice is choose the attributes. What attributes you really want to consider, and how much weight you want to give to that attribute. That's always the #1 choice question. And then after you finish the choice of your attributes, the next question is what kind of distance formula you're going to use. I told you you have a Euclidean distance, you can cosine distance, Jacobian distance, Hamming distance, whatever. There's tons of those. And choose the right one. The first choice, you can always try to Euclidean distance. But look at the scale of the attributes. That's very important. Typically, unless you really want to give one attribute a huge weight, you can give the weight explicitly. However, you don't want to give unintentional weight. What's the unintentional weight? Now, the example is this. If you consider a person's height, the height changes not much variation from 1.5 meter to 1.8 meter. But however, people's weight has a huge variation from 90 pounds to all the way 300 to 500 pounds. And that if you look at the bonds or stock, the capital could go all the way from few million dollars to hundreds of billion dollars. So if you put those raw number in without normalize it, all the other variables is going to be invisible. Are you with me? Because their difference is huge. You compare one company maybe have 3 million asset, the other company maybe have 10 million asset. And the 10 minus 7 millions, if you square root, all the rest doesn't matter. Like the tenure of the CEO and the average salary and all the things is kind of drawn, by this asset. So that's a kind of a baseline knowledge for you to do in those data mining. You need to normalize it. How? For the height, you look at the average height, you look at how many deviations. If 1.5 meter, you might think that this is just one deviation from the average. 2.1 meter, maybe too high, is 2 deviations in the other side. You normalize into the average is 1, then the deviation goes to the other side, plus minus sigma. And then, doesn't matter what variable numerical you want to compare, you always compare is the average or small size or big size or huge size. It depends on how many scales you want to make. It's better to keep the numerical number because the numerical number has more accurate information. But nevertheless, you normalize it. You don't have to put it in big cap, small cap, middle cap. You lose information there. But you normalize it. With the average cap, then is how much deviation from that. Okay. Another key is how do you normalize those attributes? It's most important. After you normalize all those things, and then you're going to use that distance formula. That's the attribute of your I attribute, Q attribute. P and the Q are the 2 cases. And the P maybe is what you know, Q is what you don't know. You always compare to what you know. And this sigma, you just add all the attributes difference. You look one by one and just sort the distance from the, maybe if your k equal 5, then all you need is the top 5 nearest. The rest you don't need to calculate or keep. So when you add this square root, that's a Euclidean distance. And then you got all the, let's say your k equal 5, you got the 5 shortest distance. And then you're going to check what class this 5 belongs to. If 4 of the 5 belongs to positive, 1 belongs to negative, of course the vote result is positive, right? So, or vice versa. And then another way is give different weight to the voter. Maybe somebody has more power because they're close, and more similar, and some a little bit far away, even is in the voting right, but they have less vote right. So that is it 1 over d squared. You already calculated the d for each case, right? So 1 over d squared, what is that? That's the reverse distance squared, right? The reverse distance means the far away you are from my test case, then the less influence your vote will become. The more close to my vote case, almost identical, then you have more voting power. That's how you measure the value of the house, right? It's a rich family, it's a rich area house or it's a poor area house. It depends on distance, reversed. Normalize the data. But that could be very counterintuitive. And the first of all, as I said, you need to know your data. If you are looking for this bits, the digit bit, and the distance from this two, but the Euclidean distance are both 1.4 square root of 2. You see the only two bits are different, right? Right. But if you look at the number, that's very counterintuitive. That's a very different number. Look at that. You can look at this as a 1 trillion. This is just 1. If you're talking about a number, of course, you're not going to use that distance, right? It really depends on what you're talking about. And if that's make sense or not make sense, it's all under the application context. If you don't understand that, the machine won't get anything out of it. So look at those. If you say the distance is square root of 2, really depends on what you're talking about. And also normalize in the unit lengths. What means unit lengths? Means like the capital and the mean also be 1. How about that? If the mean is 1, like a cosine distance. Remember cosine distance? We always looking for the unit, each attribute will be end up with the unity vectors 1. That's the only thing is your direction.